into which or over which has been placed a little object with an arrow on it. The object with an arrow, you can see some sort of a pattern on a piece of paper or a screen. What I want to do, may actually need to adjust this a little bit to get it to actually work. Let's see. Here we go. A little better. And I need stands. What I want to do with it is try to image it onto a wall, for example. Attempt to do it. Using this guy. It's pretty blurred by the time it gets to the wall right now, but you can see that there is some semblance of this crossed arrow thing. I'm just going to go ahead and move it up just a little. And what I have is one lens, which I can place in the system somewhere. Here, for example. And with that one lens, I can somewhere create a nice sharp image of the object. And so, for example, there's a fairly sharp image here that goes away if I take the lens out. Here it's blurred. Here it's sharp. So the introduction of the lens into the system allows me to form a nice sharp image somewhere. And if I move the lens around, then it moves where the image is formed. So for example, if I move the lens to here like this, I get an image that's formed very close to the lens. If I move the lens out here like this, I still have a reasonably sharp image all the way out here and a reasonably large image all the way out here. Don't know if you guys can see that very well from where you all are. It even forms reasonably nicely on the wall. And if I turn off the overhead projector, I might be able to put it on the screen for you. You see there on the screen a nice sharp image of this crossed arrow thing that I've introduced to my system. And if I take out the lens again, blurred image. Sharp image again. So what we want to know is where does the lens have to be placed in order to form that sharp of an image? How much magnification does that image give to us? So this track actually has on it a sort of built-in meter stick. And my object is at the 30 centimeter mark. my lens, as it turns out, is about the 38.5 centimeter mark. And if I look on the lens itself, it says that it's a 75 millimeter focal length convex lens. So we're talking 7.5 centimeters. Now you saw how far away the image was formed. Talking a distance like about this. This is maybe 1.25 meters, a meter and a half. Guess I could use this guide to approximate it better. So there's 70 centimeters. Plus an additional 45. So if you consider that there's a little bit of an angle in here, maybe about 1.2 meters is where this image is being formed. So what we want to do is we want to draw a ray diagram and use the thin lens equation to try to predict or try to verify, does the image actually get formed where these equations and predictions say they should be formed. Also, and this is our first quiz question, you all saw the image, I hope, or paying enough attention to see the image. So I want to know what kind of image it was. And there are what kind of image was formed. There are some options here. So I'm going to make this like a short answer and essentially select the letters that go with the options that match the image. So A is real. That's as opposed to virtual. B is larger as opposed to smaller than object. And C is upright as opposed to inverted. And D, if none of these are true, then you have none of the above. So you have to select all the letters that go with the correct answer. So if it is a real, larger than object, upright image, you'd have to put A, B, C. If it's real but smaller and inverted, then you just put A. Most people correctly identified it as real. It is, because if I can put it actually on the screen, meaning if I can put a screen there and the image appears on the screen, it's real. Only 2 people identified it as larger than the object. This little thing is the object. This is the image that's being formed by that object. Is that larger or smaller than the object that I just showed you? Well, it's taking up like a whole handbreadth of space here. So if I move this thing over here, you can see it's rather smaller than my hand. So that means that the image is larger than the object. So we need A and B. And then the last thing it asks is it upright or inverted? That one may be a little harder to tell from where you are. The main hint is that you can look and see an arrow point like this. And on the object itself, that arrow point is here at the top, but on the image it's here at the bottom. So that means that it is also an inverted image. So the answer must be A and the B. Now, just for fun, I brought an alternative means of attempting to image this thing, which is a brighter light source known as a laser that is expanding through. Now, the laser unfortunately doesn't fill the whole cross. It's a pair of crossed arrows. But we can illuminate different parts of it and see that it's a pretty sharp image here. It means that it's correctly imaging it to there. And again, this should look substantially larger than the object which is actually being illumined, which again is this little crosshair in the middle of this square. Alright, so now we can go and draw our ray diagrams. Last time I showed you how to draw the ray diagram for a mirror, a spherical mirror. So this time we want to look at what does the ray diagram for a lens look like and what is the equation for the lens. Actually, we'll do the equation for the lens first because it should look familiar. It actually looks like the same equation that we just used for the mirror. 1 over dO plus 1 over di equals 1 over f. Same as with the mirror. There is some small subtle differences in as much as the sign on di and the sign on f don't go with the same shape and with the same location relative to the optical element as with the mirror. In the case of a mirror, the focal length was positive if you had a concave mirror. So for mirror, this will be f equals positive. This will be f is negative. For a lens, this one right here goes with f is negative, and this right here goes with f is positive. Where the arrow that I've drawn in each case is showing which direction the light is incident on the optical element from. So the shape differs between the two, and that's largely because in the case of a mirror, we're imaging via reflection, whereas with a lens, we image via refraction. The common theme to the sign of f is that if f is a positive number, if the focal length is positive, then this optical element will cause a beam to focus. All Alright, so in the case of a mirror, if you have a mirror like this and you send in a beam of light like this, the beam is going to reflect like this. It focuses. In the case of a lens, if you have a lens which is concave like this and light is incident on it, it will leave like this. It means it defocuses. That's why this one has a negative focal length and this one has a positive focal length. Focal point is here. Focal point for this one is actually a virtual focal point. Basically, you have to draw virtual lines like this to locate the focus, which would be right here. Okay, and then likewise, for this kind of a mirror, a convex mirror, you send in a beam like this, it will reflect away, like this. And so you get a virtual focal point. So this is a negative focal length mirror. But if your lens is like this, you send light in, light is going to refract through this surface so that it's nearer to the normal. And so what you end up getting is that the rays do something like this. You get a positive focal point. All right, so that's the sign convention for the focal length f. The other sign convention is the one that goes with the image location. And again, basically what it means is if DI is positive, then you're going to get a real image. If DI is negative, you're going to get a virtual image. So in the case of a mirror, a real image has to be formed somewhere where light really does pass through. That means that it's got to be formed somewhere on this side of the mirror, same side as the object is on. In the case of a lens, the image needs to be formed on the opposite side of the lens from the object in order for light to actually pass through it after interacting with the optical element. So those are your sign conventions. Now what about drawing a ray diagram for a lens? How do we draw ray diagrams for a lens? Well, as with the mirror, we begin by defining our objects, optical elements, etc. And we need to draw for ourselves an axis that will be the principal axis, just as we did with the mirror. That axis goes straight through the lens. We also need to define for ourselves a focal point for the lens. And actually you draw two focal points, one on either side of it. They're both the same distance from the lens as each other. From there, you have to draw your object. Now, on this one right here, these two numbers combined give us our object distance. So DO in this case is 8.5 centimeters. That means that the object is somewhere over here on this side of the lens and on this side of the focal point of the lens. It's farther away than the focal point. So what lines do we need to draw for this? There's actually three that make some sense to draw. With the mirror, we had 4 lines that we could draw. With this guy, there's actually 3 that are reasonably easy to draw. And you can make the lens arbitrarily large in order to fit all of them, even if the lens isn't actually this big. So, first line that you can draw is parallel to the principal axis, like this. Where will that ray go after interacting with the lens? It has to go through the focal point. It has to go through the focal point because it's parallel to the principal axis, and if we drew just a bunch of rays that are parallel to the principal axis, they all go to the focal point, and that's how we define where the focal point was. All right, second ray we want to draw actually going through this focal point right here. So it starts off here, passes through this focal point, and then hits the lens. What is this one going to do after hitting the lens? Well, it's basically going to do the opposite of the first one that I drew. It's going to refract so that it's now parallel to this principal axis. So my refracted ray basically comes off like this. I should extend this line a bit. Maybe extend this line a bit. All right, third ray, what we do is we draw it so that it hits right where the middle of the lens is, or right where the principal axis on the lens is. And that line is sort of analogous to the radial line with the mirror. It's not going to have any deflection as it refracts through the surface of your lens. So one line should go through this point and just continue as a single straight line. You see that all three have arrived at the same location on the diagram. So that means that the image has to be formed where all these meet. And you see that what we get is, A, that the rays really did cross there, so it's going to be a real image, as we saw when I projected it onto the screen. B, the arrow is reversed from how the object is. My object is here, my image is here, and it's upside down. And finally, you can see that this object is considerably smaller than this image. In this particular case, it's about a factor of 4 smaller. Okay, so it's a magnified image. What is the magnification going to be for the lens? Well, you use the same equation that we used for the mirror. You use magnification is defined as height of image divided by height of object, and it happens to be equal to, geometrically it is equal to, the distance to the image divided by the distance to the object. So again, here is a DO, distance to object, and then this distance right here would be DI. Focal length would be the distance from your lens to your focal point, F, defined in this equation. So let's use this equation and see where it predicts the image to be formed for the setup that we have here. This one right here, we can rearrange to say 1 over DI is 1 over F minus 1 over DO. So given the numbers that we have here, we have a 1 over 7.5 centimeters minus 1 over 8.5 centimeters. So this is predicting that the image distance is how much? The answer is not just 8.5 minus 7.5. We have to invert stuff, subtract it, then invert it again. loaned out my normal calculator to somebody else, so bear with me. One over DI would come out to 0.01566, blah, 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 inverse centimeters. So if we reciprocal that, we end up getting about 63.8 centimeters is the distance to the image. Now we measured a moment ago that this was collectively 171 centimeters, but I had measured it from the back of this, so I need to subtract that distance from where the object is. Looking at the scale here, that means that the actual predicted is more like 70-ish centimeters. So within about 10% between measurement and theory calculation. And that 10% is not unreasonable because these lenses have some tolerance to them. If it says it's 75 millimeters, it's often 75 plus or minus like 1 or 2 millimeters, which can very quickly have a large difference in where the image is formed. So what kind of magnification does this thing predict? Well, magnification is negative DI over DO. So we're looking at 63.8, negative 63.8 centimeters divided by 8.5 centimeters. So if we throw that into our calculators, divide by 8.5, we get 7.5. Well, negative 7.5. So what does that mean? It means that the image should be about 7.5 times larger. The length scale stretches by a factor of 7.5 as compared to the object. So looking at this guy here, we said that it's about the same, the image is about the same size as my hand span. So there's 1, 2, 3, 4, 5, 6, about 7 of these in my hand span. So again, within a factor of about 10%, calculation and experiment agree. What happens if we use a defocusing optical element rather than a focusing optical element? What happens, in other words, if we choose a concave lens or a convex mirror? What we end up getting is a virtual image in both cases. And it is a virtual image which is smaller than the object itself. That also means it's nearer to the lens than the object itself. This one right here shows 2 of the 3 possible rays that we could be drawing. The third ray is one which would essentially be aimed at this guy right here. But what happens happens is that when it passes through the lens, it deflects. So if you want all three possible rays for this diverging, they are as follows. There's one that passes through this guy, and then, whoops, not this one. This one is a bad one. There's one that is parallel, and it deflects such that the virtual lens, the virtual ray, would have passed through this point. Second one is like so, with no further deflection. The virtual ray of it basically matches the real ray. The third one does like this, but the virtual continuation, if you continued this line, would have passed through the focal point. So those are your three rays if you want a diverging lens. And again, this one right here, the virtual ray passes through the same point, and so that's where your image is formed. Why draw three lines, by the way, instead of two? Well, the third line sort of serves as a double check. You need two, and where the two cross, really or virtually, is where your image will be formed. But if you have a third one, it should also cross at the same location as the other two, and that should be where your image is. So if they don't cross in the same spot, you may have drawn one of them wrong, and you now have a double check to show you that something is wrong. That collectively is it for imaging. What we have next is wave optics. Wave optics basically means interference, because we've passed through a set of slits. It means diffraction, because we've passed through a single slit. And it means spectroscopy, possibly, because you can use diffraction for that purpose. There's also one other property which is only lightly shown in here, and which I will demo for you all today, because I have the equipment on me to do the demo. And this is what's called polarization. And the way that we want to do this is, I have a laser that's set up here. I turn on the laser, you get a spot that's over there somewhere, and I can actually try to raise the spot a bit. Not going to raise enough to put onto the projector like that. I'm going to have to undo some of these. Go. What I have is a pair of optical polarizers. If I take one of these optical polarizers, just one of them, and place it in, like so, you still get the beam. Still makes it through, no problem. If I take a second one and place it in, and I place it at the same orientation as the first one, you still get a beam that makes it through, no problem. However, if I rotate one of these, the beam can be made to disappear. In fact, you can see it get dimmer as I rotate it until right about there. And if you look very closely, you can still see the beam here, but it's virtually gone at this point. And if I rotate a little more, I may be able to make it really vanish. So even standing close up, I can't see it anymore. All I've done is just rotate a piece of plastic, essentially. And yet, the beam vanishes when I do that. Why does it do that? Any ideas? And again, if I turn this piece of plastic the other way, or if I continue rotating it, the beam comes back. It's gone again. Rotate it some more, it comes back. Now it's gone again. Back, and so on. There's actually two angles for which it completely vanishes, as it turns out. If this one is called 0 degrees, then this one will vanish at 90 and at 270. In other words, the two that are perpendicular to 0. This is what's called cross-polarization. It's how your polarizing sunglasses work. Because it turns out that when sunlight reflects off of stuff, like the ground or water or so on, it tends to be strongly polarized. And so if your glasses have the right orientation, they'll block out all the reflected light. What basically happens is that these two pieces of plastic are made from long-chain polymers. And those long-chain polymers can vibrate when the light passes through them, if they are oriented in the same direction as the light beam happens to be oriented. And if they vibrate, it basically means that you are accelerating some electrons that are inside of the polymers. And by accelerating those electrons, you have to absorb some amount of light. And so they basically absorb light as they're accelerated. But if they are arranged perpendicular to the direction that the light itself is vibrating in, because light is a wave, so in fact a transverse wave, if they're oriented perpendicular to the direction of light's vibration, then they can't really vibrate themselves, and therefore they will tend not to absorb very much light. And so all the light makes it through. So not only do they help you out with polarized sunglasses, they actually can be used for microscopy purposes. Polarized microscopy is one of the fields in microscopy that has become kind of big of late. What you can do with it is there's certain materials that you will not see under a plain old microscope, that if you put a pair of cross polarizers under the microscope, you will see patterns show up that you wouldn't have seen otherwise. Those patterns are really there. As one example, has anybody ever looked at a potato under the microscope? Take some potato and smear it on a microscope slide and look at it under the microscope. You'll see a bunch of granules that look basically like this. Under plain light, and you might see a little bit of speckling and that kind of thing in them, but more or less they just look like empty granules. If you put a pair of polarizers on them, a pattern actually appears. You get a pair of dark lines cross because they often look like a stylized cross, like what was worn by the Knights of Malta. This thing that I'm coloring in white is actually the part that's dark shaded, for what it's worth. But you get a pattern like that. It's basically a starch indicator. So you get this in potatoes. You can also get something similar with apples or with a plantain or anything like that that has a lot of starch to it. So it's something you can use in microscopy as well. I think that's enough for today.